So today we're going to be learning about single displacement reactions. A single displacement reaction is when you have a single element. So let's say this element C here is on his own, and he's kind of lonely, and he sees elements A and B are happily bonded in an ionic compound. And so element C sneaks in over here, he bumps out element B and steals A for himself. Now B is single and alone, and element C is happily bonded to element A. So that's a single displacement reaction in general. There's two different ways you can do a single displacement. One is by displacing with a metal, and the other is by displacing using a nonmetal. So first, if the single element that's coming in to destroy a nice little ionic compound is a metal. So if you've got a single element that's a metal, there's actually three things it can do. The first thing it might do is it might displace another metal in an ionic compound. So this is where you have metal 1 comes in here and sees metal 2 happily bonded to a non-metal. That metal 1 will come over and bump out your metal 2 and steal the non-metal. That's our first possibility. The next possibility is if you have metal 1 sees an acid, so a hydrogen bonded to a nonmetal or bonded to a polyatomic ion, then that metal will come in and bump out the hydrogen from an acid. So that's our next possibility. A single metal will bump out the hydrogen and displace the hydrogen from an acid. The third thing a single metal could do, if I have metal 1 coming in here and it sees some water, can actually bump out the hydrogen from water, but I'm going to write the water in a weird way. So normally we write water as just H2O, right? But I'm actually going to write it as HOH, or in other words, a hydrogen bonded to a hydroxide polyatomic ion. Of course, that is just H2O, right? There's two H's and an O here. It's the same compound, it's just water. But I'm writing it differently intentionally to show you what's going to happen in this reaction. When we do a single displacement with water, that metal's going to come in here and bump out that hydrogen and bond itself to the hydroxide that's left behind. So hydrogen gets bumped out, and hydrogen is the single thing again, but now that metal is bonded to the hydroxide. So the third thing a metal element can do is displace a single hydrogen from water. The second kind of single displacement reaction you might get is a nonmetal doing the displacing. So if the single element is a nonmetal, you can also do a single displacement reaction that way. In that case, your nonmetal will displace another nonmetal in an ionic compound. So this is where you have nonmetal 1 sees a metal bonded to nonmetal 2. That nonmetal 1 comes over and bumps out nonmetal 2 and bonds itself to the metal. And that's our second kind of single displacement reaction. Let's look at a few examples just to make this a bit clearer. So first we have copper. Copper is single. Its charge is going to be 2 when it forms a bond, but we're not going to write the 2 down in our balanced chemical equation here, right? Because right now it's just a single element, and copper is not diatomic or anything funny like that, so it's just copper. If you want to write the state, it's a solid. It's going to find maybe some silver nitrate in solution. Nitrate is NO3. If you remember, its charge is -1. Silver, if we can check on our periodic table, is a charge of +1. So these are just going to be a ratio of 1 to 1. Silver nitrate, that's its chemical formula right there. When those two meet, what that copper will do is it'll come over, see that silver nitrate, and it's going to bump it away and bump the silver away and steal the nitrate for itself. So the copper steals the nitrate, steals the polyatomic ion, or if it was just a nonmetal there, it would steal the nonmetal, and bumps the silver off on its own. Now let's watch our chemical formulas carefully here. Copper has a charge of 2, nitrate has a charge of -1, so I'm going to have copper nitrate, and we'll need 2 of those nitrates for every 1 copper in order for everybody to have a full valence shell. Now silver isn't diatomic or anything fancy, so it's just going to be a single silver like that. So I can first check all my chemical formulas, they're all right. Then the next thing I can do is balance this once my chemical formulas are solid. So it looks like copper's good, 1 copper on each side, 1 silver on each side, but the nitrates are not good, right? I've got 2 nitrates in the product side and only 1 in the reactant. So I'm going to need to put a 2 in front of the silver nitrate. But now I have too many silvers, so I'm going to need to put a 2 in front of the silvers on the product side. Coppers are still good, 1 copper on each side, so that is all balanced. So that's how a single metal can come in and bump out a metal in an ionic compound or a polyatomic ionic compound. Next, let's look at how a metal like magnesium can come in and bump out the hydrogen from an acid. So here's magnesium, and here's hydrofluoric acid is HF, right? H has a positive 1 charge, F has a negative 1 charge here. So it's just going to make a ratio of 1 to 1 here, HF. That magnesium can bump out the hydrogen in the acid. When it does that, magnesium will steal fluorine and leave the hydrogen on its own. Now let's watch out for our chemical formulas before we go any further. Magnesium has a charge of positive 2 because it's in group 2. Fluorine has a charge of negative 1. So we're going to need 2 fluorines for every 1 magnesium atom here. And that's my new ionic compound. And hydrogen over here, hydrogen is on its own, but watch out, hydrogen is one of those elements that's part of our 7 diatomics. So hydrogen will form H2. So hydrogen is diatomic. So anytime you see hydrogen on its own as a single element, it's going to link up with another hydrogen and form H2. It's a diatomic gas. So you're going to make sure you write that as H2. Before we go any further, we've got to balance this. I have 2 fluorines on the product side, only 1 on the reactant side. So I'm going to need to stick a 2 in front of my HF. Now I can check hydrogens. I've got 2 on the reactant side now and 2 on the product side, so they check out. Magnesiums, I've got 1 on the product side and 1 on the reactant side, so we're good for magnesiums. That is all balanced. All right, last but not least, barium runs into some water. So whenever we're doing a single displacement with water, it's a really good idea to write your water, instead of as H2O, write it as HOH, or at least think this in your brain. You don't have to write it down necessarily, but think of it as an H bonded to an OH. It's still H2O, but it's just H bonded to OH, that hydroxide group. Because then what will happen is we can see barium's going to come in and bump out that H, that single H, and steal the hydroxide group for itself. And that's what we'll get. So that barium comes in, this barium comes in, bumps out the 1 hydrogen, and steals the hydroxide. So we get barium hydroxide. We'll watch out for a chemical formula in a second. That hydrogen gets bumped out and it's on its own. Now let's do our chemical formulas. Barium has a charge of 2. Hydroxide has a charge of negative 1. So I'm going to need 2 hydroxides for every 1 barium. And hydrogen, we said, was diatomic, so that needs to be H2. Now let's try and balance this guy. There's 1 barium on each side, so that's all good. There's 2 oxygens in here, and there's only 1 oxygen here. So I'm going to need to stick a 2 in front of my water in order to get enough oxygens on both sides. Now I have 2 hydrogens here, 2 hydrogens there, and 4 hydrogens there. That's all balanced and good to go. Now the next question we have is, how do you even know that a single displacement reaction will happen? It's not just like you can mix any old metal with any old ionic compound and that metal will displace the metal in the ionic compound. That doesn't happen in every reaction. You have to figure out before you even start to do a single displacement reaction, will this happen? How you know is you use what's called the metal activity series. So this is anytime you're looking for, does a single displacement happen with a metal replacing a metal or hydrogen? That's where we use the metal activity series. So if the single metal is higher in the activity series, that means that the single displacement reaction will occur. So anybody more towards the top here is more likely to bump out any metal that's below it on this activity series. So basically think about the non-metals or the polyatomic ions as preferring everybody at the top over anybody at the bottom. So for example, if I have barium chloride, then the only things, so here's barium on the activity series, the only things that are going to bump out of barium from barium chloride would have to be potassium or lithium. Chlorine would prefer potassium or lithium to barium, and so those two will be able to bump out the barium and bond to the chlorine. But anybody below barium here is not going to have any success. Now notice you'll see hydrogen shows up here twice, right? So here's hydrogen in water, and here's hydrogen in an acid. What this is telling you is that hydrogen in an acid is easier to bump out. So say you have something like sulfuric acid, so H2SO4, that's sulfuric acid right there. If we have maybe copper comes along, tries to bump out that hydrogen in sulfuric acid, it's not going to work because copper is below hydrogen on this activity series. But if I have somebody like maybe iron comes along, tries to bump out that hydrogen in the acid, that will totally work. That iron is going to bump out the hydrogen and bond to the sulfate, and you'll get iron sulfate and hydrogen gas on its own. But if we have a hydrogen in water, so an HOH, that's water, and you have iron comes along to the water, well, that's not going to have any success in bumping that hydrogen out because notice how iron is lower than hydrogen in water. The only way you're going to be able to bump out that hydrogen in the water is using any one of these ones that's above hydrogen in water. So sodium, calcium, barium, potassium, or lithium would all work. If we brought a sodium in, that sodium would be able to bump this H out and bond to the OH in the water. But nobody below this hydrogen and water point would be able to do that. So that's how our activity series works with metals.